It's clear that rising levels of greenhouse gas emissions are warming the planet and triggering profound environmental changes. What is less understood is exactly how the climate systems that govern our weather are being disrupted and how much worse things will get in the years and decades to come. For some answers, I reached out to a climate expert, Dr. Jennifer Francis of the Woodwell Climate Research Center. Thank you for joining me. Welcome.
Pleasure.
Woodwell was named the top climate change think tank in the world for 4 straight years from 2013 to 2016. This first part of our conversation, linked below, is a brief crash course on how we've reached 1 degree of warming so quickly.
20,000 years ago was the last ice age that the Earth experienced, and that's on the left-hand side of that graph. We've basically been warming up. The big ice sheet over North America retreated. And pretty much since 8,000 years ago or so, we've been living in a fairly constant global temperature with a slight cooling starting to happen. And that whole piece of the temperature record is all controlled by natural processes, things like changes in the tilt of the Earth's axis relative to our orbit around the sun, changes in the Earth's orbit around the sun, things like that. So, of course, we weren't around before several thousand years ago, but all of those changes that we observe back in time there are just caused by natural effects. But of course, what's happening just in the last century or so is this huge digression from what would have been a continued cooling trend, and instead we see this huge spike in warming.
The evidence is in the ice cores. By extracting and analyzing a column of ice that hasn't been exposed to air since it was frozen, the exact makeup of the atmosphere back then is revealed.
The unique things about polar glaciers is each year that it snows there, the snow never melts. So you get 1 year of snow on top of the next year of snow. It compresses, so everything that fell out of the atmosphere, dust, salt from the ocean, volcanic ash, is preserved in that ice core.
Sure enough, these ice cores show that greenhouse gas concentrations fluctuated within a tight range until innovation allowed us to use an increasing amount of coal, oil, and methane gas. This terrifying visualization shows how fast observable temperatures have risen since we began deviating from the stable, natural cycle revealed in the ice cores. And as human activity has increased, so have the types of greenhouse gases we emit and how we emit them.
We know with 100% confidence that this is being caused by human factors, which include not just the burning of fossil fuels and contributing greenhouse gases to the atmosphere, which of course trap the heat, but also things like deforestation and changes to the land surface.
The effort to prevent catastrophic warming culminated in 2015 in Paris, when the world set the long-term goal of limiting the increase in the average global temperature to well below 2 degrees Celsius by the end of the century.
The Paris Accord, the design of that is to try to keep the globe under 1.5 degrees Celsius warming if possible, and certainly below 2 degrees Celsius, because we believe that beyond 2 degrees is really catastrophic in many ways.
But the Paris Agreement left each country to set up their own emission targets and report their own progress. On top of that, there isn't even a mechanism to force countries to hit these targets by any specific date. Although President Trump has withdrawn the United States from the agreement, President-elect Biden has pledged that the United States will re-enter it the first day he takes office in January. It is unclear, though, if Biden will be able to strengthen the agreement further, although it is clear that the world quickly needs to.
Some areas of the United States have already warmed beyond that limit that we're trying to keep the globe under.
Well beyond.
Well beyond, exactly. And if you were to look at a graph like this for the Arctic, you'd see almost the entire Arctic has totally blown by the 2 degree mark. So the story here is that, we're on a trajectory right now that is not very good. It's pretty pessimistic in terms of trying to keep to the Paris Accord unless we take very strong action very soon.
The vast, deep oceans absorb nearly 90% of the heat that is trapped by greenhouse gases, and warming temperatures are causing the sea and land ice to melt faster than it otherwise would.
There's two things going on there with the oceans. One is they absorb some of the carbon dioxide into the water itself, contributing to ocean acidification. So the oceans are becoming more acidic over time. But then the other factor is that the oceans absorb almost 90% of the heat that's trapped by greenhouse gases. Those red and yellow colors showing how much warmer the oceans are than they should be compared to a reference period over about a 30-year time period. And the warmest ocean areas are off of the west coast of North America, all around Alaska, all around Greenland, and all along the coast of the Arctic as well. We're seeing the impacts of these very warm ocean temperatures, especially around Alaska, and they've had a record-breaking warm all month since the winter. If they haven't been record every single month, they've been very close. Wow. The sea ice in that part of the Arctic has been at record low levels all winter long, all spring long, all summer long, especially in the Bering Sea area, which is that region right around Alaska there. In terms of the volume of sea ice, we've lost about 3/4 of it. So volume, of course, includes the area of the ice times the thickness of the ice. In the upper right corner of this image here, you can see most of the Arctic Ocean filled with ice. During September, which is when we typically see the ice reach its smallest area, after having gone through a whole summer of melting. And in the bottom graph there is showing what it looked like in 2012, September 2012, which was when we've had the least amount of sea ice ever recorded. And it's approximately half of what it was back in the late 1970s and early 80s. And again, that's just a huge difference in a very short time. And that red and orange color area there is showing you where the ice used to be, and instead now is open water. And of course, the ice is very reflective. Most of the sunshine that hits it gets reflected right back to outer space, and so that energy never gets into the climate system. But now we've lost so much ice that instead of having that bright white surface there, now all that extra sun's energy goes into the water, warms up that water, and then helps contribute to more melting of the sea ice. And this is one of the reasons why the Arctic is warming so much faster than elsewhere, is because of this extra energy from the sun that now is getting absorbed into the ocean when before it was reflected right back to space. Now ships can get up in there and not worry about running into ice so much. So there is this opportunity to go up there and drill for oil and excavate other mineral resources. And there's a lot of countries that are looking north and seeing opportunity.
The big landmass on the left is Little Diomede Island. It's U.S. territory. On the right, a little bit further away, is Big Diomede Island. That's Russian territory. So this is really the front line in what is an increasing competition for the Arctic.
When land ice melts, it flows directly into the ocean, adds mass to the ocean, and contributes to sea level rise. When sea ice melts, which is the ice that's already floating on the ocean, that does not affect sea level rise because it's already floating and already displacing ocean water. So that melting land ice, and that includes glaciers as well, is one of the biggest contributors to sea level rise, and we're seeing it increasing.
Is there around 7-8 meters of potential sea level rise on Greenland alone?
Yeah, that's about right. 20 feet.
Oh.
7 meters, yep.
Wow.
That'll happen relatively slowly, but we probably won't see that whole Greenland ice sheet melt in our lifetimes, but we're on the right track for that to happen ultimately. And that is just really bad news. And that, never mind Antarctica, which holds even more ice, which is the ice sitting on top of the Antarctic continent in the southern hemisphere. And we're also seeing very clear signs of it melting as well, but mostly from the underneath. So where warmer ocean waters are coming into contact with the glaciers that come off of the Antarctic ice sheet.
The melting happening underneath the ice sheets of Antarctica and Greenland is key. Hidden from plain sight, it can cause changes that seem sudden and random, but that can actually be predicted if studied in the right way. This is the focus of University of Copenhagen professor Jorgen Peter Steffensen.
So right now, I think the contribution of Greenland ice sheet to world sea level change is just beginning to show, but we don't know if this shrinking is going to be a linear, straightforward process that you can predict. You can monitor the surface. Trouble is, all kinds of funny stuff is going on at the base of the ice sheet.
If something odd is going on at the base in these ice streams, and there are a lot of ice streams in Western Antarctica too, then it can upset the entire apple cart. All of a sudden you would have an unstable ice sheet that might break away, not over several centuries, but over a couple of decades. And that would be disastrous.
Global weather patterns are regulated by ocean currents, but warming water is causing those currents to change. This is one of a handful of Earth system tipping elements that climate experts fear could set off incomprehensible devastation.
I'm sure most people have heard about the ocean conveyor belt, which is basically the system of ocean currents that flow all around the world's oceans. There are two places really that push that current to flow. One of them is in the North Atlantic. And the idea here is that when fall and winter come along, the ocean surface waters get cold and they freeze. And when they freeze, they eject the salt out of the water. And that heavy, salty, cold water that comes out of that freezing process is very heavy relative to the other water in the area. And so it sinks really rapidly. And it creates this downward flow of water, which then basically turns south and starts heading towards the southern Atlantic and meets up with other currents along the way. And another area where this happens is off the coast of Antarctica, where also you get some very cold air temperatures and ocean water freezing. So the concern is that in the area around Greenland, the water has been becoming fresher, partly because of the water that's being melted from the Greenland ice sheet.
Over the past few days, we've seen a significant amount of actually liquid water on the surface that has both accumulated in small ponds and probably approaching the size of lakes, especially near the edge of the ice sheet. An interesting thing is that the melt season actually in Greenland started pretty much end of April, beginning of May, which in the grand scheme of things is very close to a month earlier than average.
My name is Brooke Medley. I'm the Deputy Project Scientist for Operation Icebridge. Last April and May, we were actually flying in Greenland out of Kangerlussuaq on the NASA P3. This was somewhat of a unique year where we expected to be going early enough where we would see the typical dry snow conditions, but rather we were met with a much different scenario where we saw all these spectacular blue ponds of beautiful liquid water just pooling on top of the surface.
The ice sheet is actually experiencing almost an additional month of melt because it started so early here. Part of it is actually driven by the fact that it's very warm right now, but also that there was not a lot of snowfall last winter. And so what that means is when the snow does melt, it very quickly exposes darker ice, which can then melt even faster. Just a significant increase in the total amount of water that we just see in general.
Over the course of 2019, there was so much melt that it actually ended up being the second largest meltwater production year for the Greenland ice sheet since 1980. It's actually quite simple. The longer your melt season, that means you can just have more time to accumulate more melt. And the only place for this water to go is into the oceans.
Also, there's more fresh water flowing from rivers into the Arctic Ocean. That fresher water then comes out into the North Atlantic in that passage between Europe and Greenland there. And so we're finding this area of fresher than normal water just south of Greenland. And the reason it's looking colder than average there is because when that fresh water is sitting there, it floats, because fresh water is lighter than the salt water. It sits on top and it prevents that freezing process and that creation of that very salty, dense water from happening. It slows it down anyway.
You can see that on the map, that's the most rapidly contrasting color area.
Exactly.
It's very clear.
Yes, it is. And it even has a name. It's called the cold blob.
The cold blob.
Yes, it's a very technical term.
Because it just sits.
Yeah, it's been there for several years. And it's a very interesting area. A lot of people are studying it because not only does it have this effect on the ocean circulation, but it also is causing weather patterns to change in the North Atlantic and in Europe. Because whenever you change temperature patterns in the ocean or on land, you affect winds. And when you affect winds, you affect weather.
The water moving through the Atlantic meridional overturning circulation flows at a rate of 20 million cubic meters per second. Studies show that since the 1950s, this rate has slowed by 15%. That 3 million cubic meters per second loss is equivalent to 3 times the flow rate of all the rivers in the world. If this already massive decrease continues, which seems likely, and the AMOC stalls completely, it would disrupt the entire climate system. And we know this because it's happened before. Past changes in Atlantic overturning have caused some of the strongest and most rapid climate shifts, such as a southward shift of the tropical rainfall belt and warming of the Southern Ocean and Antarctica.
The last 11,000 years, that's since the Ice Age, our interglacial period, has been unreasonably stable. And we don't know why. With an enhanced greenhouse effect from burning of fossil fuel, CO2 and methane and so on, you would have a gradual increase in temperature. That's what all the models show you. It's sort of a gradual increase in temperature. But that's assuming that the climate plays nice. And we actually know from the ice cores that the climate does not play nice all the time. We have tons of examples of climate changes where we see complete reorganization of the atmospheric circulation from one year to the next. And that will be extremely hurtful for any agricultural activity in the world, because the weather will change and will not change back. What we know from the sudden climate changes in the past is that these abrupt changes represent a reconfiguration of the entire atmospheric pattern. What if, with the emission of greenhouse gases, that we trigger a situation when this system all of a sudden goes into a feedback? If you reconfigure the transport patterns of high pressures and low pressure systems over North America and, for instance, Europe, but particularly North America and the Midwest, and all of a sudden it stops to rain, and it hits the Midwest in the US, and it leads to massive crop failure, that's going to impact the entire world. We don't know. We don't know where the threshold is, but we are rats inside the experiment.
One of the strongest connections between climate change and extreme weather is water vapor, the most abundant greenhouse gas.
As the air gets warmer, it can hold more water vapor in it. And as the oceans get warmer, they're evaporating more water into the atmosphere. So we're seeing a very clear increase in the amount of water vapor that's in the atmosphere, globally speaking. So it's about a 7% increase in the amount of water vapor since the 1970s or so. The reason that water vapor is so key is that it plays a number of roles in both the climate system and also in weather patterns. Water vapor is actually the most important greenhouse gas in the atmosphere. And so as we increase the amount of it, it's adding to the heat that's being trapped by the human-caused other greenhouse gases. So it's exacerbating the global warming problem. It's also the source of energy for storms. When water vapor, which is a gas, condenses into a liquid form, which you see as a cloud, it releases heat into the atmosphere. And that heat is what storms feed off of to generate their strong winds and all the other impacts of storms. And then, of course, that extra water vapor can also produce more precipitation. And so we're seeing a very clear increase in the frequency of heavy precipitation events. And these are not small increases. We're talking about 50% and higher increases in these very heavy downpours, heavy snowstorms. We're clearly seeing the impacts of this already, and there's no doubt that it's connected to this increase in the amount of water vapor in the atmosphere.
Higher temperatures, combined with more humid air, are pushing conditions beyond what the human body can naturally endure in more and more places around the world. The point you made in your talk about the health dangers that come when it doesn't cool off enough at nighttime was really important.
Sure. So on the right side of this graph is showing the fraction of the land in the United States where temperatures have been extreme during the daytime. We can see there was a very warm period back in the 30s and 40s. You can think about the big Dust Bowl out in the West that happened during that period. But then again, in the recent years, we're seeing these big spikes again in the daytime maximum temperatures. But on the left side of the graph, as you said, we're seeing a much bigger impact during the nighttime temperatures. And the reason this is so important is because, people are trying to sleep at night, obviously. And if their bodies aren't able to cool off sufficiently through sweat, or if you don't have air conditioning or some other way to cool yourself off, then there is a actual physical threshold where if it doesn't cool off enough, combined with extra humidity that's in the atmosphere that we know is also happening, then your body just can't get rid of the extra heat that it produces just through normal processes. So we're seeing this happen in many places around the globe now where it's just too hot to survive at night.
And your system shuts down. When that heat index figure goes through the roof, especially in the equatorial zones, there will be whole months when you won't be able to really work at all if you don't have an air-conditioned building.
Exactly right. And that you can pretty easily jump to thinking about migration, areas where people are already suffering mightily. And it's not just their own discomfort, but also agricultural conditions aren't suitable anymore to growing crops. You've got people who just have no way to live. They're suffering health-wise, and so they're looking for somewhere else to go. And it's very likely we're going to see migration of large numbers of people that are going to make today's immigration issues look like almost nothing. And there's clearly, I think, a climate factor, and people are starting to quantify that. So, it's not just the heat per se, but also drought. And drought has already been implicated as a major factor in the Middle East and a lot of the issues that are occurring there.
In a recent talk, Dr. Francis previewed the extreme temperatures coming soon to the United States.
So this is the number of days above 100 degrees that are projected for the middle of the century and by the end of the century. Huge sections of this country, if we stay on the path we're on, will be almost unlivable and will require a lot more energy just to be able to live in those areas. But agriculture, it's going to have a hard time.
We can expect warming combined with more water vapor to essentially shift the entire climate north by about 1,000 miles, meaning the Northeast, for example, will experience the kind of weather South Florida experiences today, and Miami will feel like the stifling hotbox that is the equatorial rainforest of South America. That's over 1,000 miles of shift.
Right. And that's just sort of the average temperature. And, it's about a 9-degree warming for Providence area, so New England basically. The average temperature is going to feel more like what Florida is experiencing now.
The region experiencing the fastest warming is the Arctic. At the same time, areas like the eastern United States have been experiencing colder than normal temperatures at times during the winter. This seemingly strange phenomenon is happening because warming Arctic air is causing the jet stream that regulates weather here in North America to behave in more extreme ways.
This is showing now winter air temperature differences from normal looking down on the North Pole. And that big red blob in the middle is just saying, hey, the Arctic is warming just crazy fast, especially in the wintertime. But interestingly, you can also see some blue colors over Eastern North America and most of Eastern Eurasia. So those areas have actually been cooling during the winter over time because of the effect of the rapid Arctic warming on the jet stream. The jet stream being this river of wind that encircles the northern hemisphere, and it takes these north-south swings as it goes around the northern hemisphere. And one of the ways the rapid Arctic warming is affecting the jet stream is to make those big north-south swings be big more often. And when we have one of those big southward dips in the jet stream during the winter, it allows the cold air from the Arctic to penetrate farther south. And we see this happening more frequently over the eastern US and over Eastern Asia in connection with this rapidly warming Arctic. When that temperature difference is really strong, then that's when we see very strong jet streams. And when it's weaker, like when the Arctic warms much faster than the areas farther south, then we tend to see the jet stream weaken. And when it's weaker, it tends to want to take these bigger north-south swings. And it's not that the storms are moving more slowly in a weak jet situation. It's that those big waves in the jet stream, like the one over North America in that picture, tend to get stuck in place for a long time. And those waves in the jet stream are really what create the weather patterns that we would see on a TV weather map, for example. So when the winds are from the northwest, like this one shows over Seattle area, that tends to be where you find high pressure on a TV weather map. And high pressure is associated with usually dry and very nice conditions. Whereas on the East Coast there, when the winds are coming from the southwest, that tends to be where the storms form. And so, as I said, when these big waves form in the jet stream, they tend to get stuck in place for days and sometimes even weeks. Whatever weather you're experiencing relative to your position in that wave, you tend to have those same weather conditions for a long time.
The jet stream is also slowing down in the summertime, causing 3 consecutive years of unprecedented hurricanes: 2017's Harvey, 2018's Florence, and 2019's Dorian. Each storm got stuck and dumped record rainfall on Houston, the Carolinas, and the Bahamas.
The slow movement of Dorian was more related to the fact that in summertime, we're seeing the jet stream weaken over the continents pretty dramatically. And the jet stream winds create the highs and the lows that steer hurricanes. In that particular case, there was a very weak high pressure area sitting off Cape Hatteras for several days. It sort of blocked it from heading north. And then that high pressure weakened, and then it allowed Dorian to finally start moving northward. So the paths of hurricanes depend completely on what the jet stream is doing. When those winds in the atmosphere are very weak, it makes it very hard to forecast where a hurricane's going to go.
And a couple years before that, Harvey just dumping feet
just a year before.
Just sitting over Houston.
Mm-hmm.
So is that what we have to look forward to, I guess?
I think we need to look forward to having it happen more often, for sure. And there's been a couple recent papers that have actually documented this trend. So it does appear that hurricanes are tending to be slower. And so the tendency for these storms to just sit in one place for a while is increasing, and it makes lots of sense. It all fits the story.
Is there a hurricane beyond a Category 5 that we could see?
Yeah, there's some discussion of creating a Cat 6. Yep, there is talk of that. Going back to that water vapor I was talking about. So when the ocean temperatures are really warm, there's also a lot of water vapor in the atmosphere, and that's the main fuel to generate a hurricane. You know, there's a lot of other factors, but the main one that you need for a hurricane to form and to become strong is that very warm water and a lot of moisture in the atmosphere.
Understanding how Earth's climate is fundamentally regulated is the key to understanding how weather is getting more extreme, and how much more extreme it'll get in the coming years.
There are some very clear connections between climate change and extreme weather. The most straightforward one is, of course, that we're warming the globe on average, and that warming is making it much more likely that heat waves will be hotter, that they'll last longer, they'll be more devastating, they'll cover more area. If you take the average temperature of the Earth and you shift it over to the warm side, then you're just making anything to do with a heat wave worse, making it more likely to have stronger droughts as well, because when it's hotter, you evaporate the moisture from the land more easily, and as soon as the soil gets dry, it heats up much more rapidly.
So recent droughts in the Southwest, or even historical droughts such as the Dust Bowl in the 1930s, these are naturally occurring droughts that typically last several years or sometimes almost a decade. In our projections, what we're seeing is that with climate change, many of these types of droughts will likely last for 20, 30, sometimes even 40 years, even exceeding the duration of the long-term intense mega droughts that characterize the really arid time period known as the medieval climate anomaly.
Of course, we're also seeing more wildfires occur because when it's hot and dry, it's much easier to have big wildfires. The next very clear connection is related to water vapor. We see hurricanes intensifying more rapidly now because they have more of that fuel in the atmosphere to work with. And we're seeing the strongest categories of storms increasing in frequency. And as that water vapor increases, we're also seeing this very clear increase in the frequency of heavy precipitation events. So those things are all very clear. They all make sense. You know, it's not hard to explain that those are happening. What's less clear, but is a very interesting and active area of research, is how these differences in warming in different places are causing things like the jet stream to change its character, and the Arctic being the biggest regional change that we believe is affecting the jet stream. We know it's affecting the jet stream. It's really just determining exactly how and in different seasons and different regions, and how much of a particular extreme event could be attributed to the fact that the Arctic is so warm or the sea ice is so diminished.
Dr. Francis discovered her passion for environmental science during a sailing trip that changed the course of her life. You and your husband, around the time you were married, you circumnavigated the globe and went to the Arctic. So you have a very unique perspective.
Yeah, that really was what got me interested in studying the Arctic atmosphere in the first place. When we went up there in 1984, that was back in the days before we had GPS and good communication, and the weather information was pretty hard to come by, and what we could get was pretty much useless. So I decided when I went back to school to study meteorology that I would focus on the Arctic.
And now seeing it sort of degrade, I'm sure, is fairly heartbreaking.
Yeah, it's amazing, actually, the changes that have happened since I was a graduate student in the early 90s. It's transformed. The sea ice is now, in terms of its volume, reduced by 75%. We're talking, a few decades. So this has an impact in many ways on the global climate system. They're not surprising, these changes that we're observing, but they're happening much faster than we thought. I'm an atmospheric scientist, so I was mostly focused on how the atmosphere was contributing to sea ice melting and other changes in the Arctic. But about 8 years ago or so, I started thinking more about how the rapid changes in the Arctic were affecting other places, in particular weather patterns down around lower latitudes where a lot of people live. And sort of going back to my training as a meteorologist during my undergraduate years, I started thinking about how weather patterns would be affected and the jet stream would be affected. And that led to a new paper that put forward a fairly bold hypothesis, I guess, that the rapid Arctic warming would lead to more extreme weather events in mid-latitudes. And that paper propelled me into this new world of science communication and talking to reporters and more public speaking.
All of these changes are clearly tied to a warming planet.
Bringing this story to public audiences where a very, very conspicuous aspect of climate change, namely the dramatic loss of sea ice in the Arctic and the warming in the Arctic, there's something that anybody could see because it's so dramatic, could be connected to what people are experiencing in populated areas, and namely more heat waves, more severe droughts, more flooding events, heavy snowstorms, wacky tropical storms. All of these very destructive effects on society.